English. Right, so where we stopped on Sunday, we wanted to see what happened in the system where when it changes its, or the system or the material is abruptly modified from one state to another. Okay, so we have phase A and we have phase B. Okay, so it can be, for example, liquid and it can be vapor. It can be paramagnetic or ferromagnetic. It can be metal and superconductor. Phases of matter. In order to study those transitions from phase A to phase B, so we know that they happen fast, usually. We know from experiment that they are abrupt. Some sort of dynamics is involved. We're not going to treat dynamics, so we at least want to understand what happens at equilibrium. So we can put phase A in contact to phase B and look what happens on the boundary between those two phases, or how those two materials, which are basically the same, but in two different states of matter, how they can coexist. Okay. So this is why we're looking on the line between them, and we know that if those two systems are in equilibrium, some specific quantities have to be constant. So for example, we know that in equilibrium, all the intensive parameters that of phase A and phase B are exactly the same. What are our intensive parameters? And T and P and mu are exactly the same for this part and for that part. Okay. Moreover, we have seen that there are stability criteria which is what they are. If we take an intensive variable and we take a derivative of this intensive variable with respect to an extensive variable conjugated to it, okay? This derivative have to be positive. So we know that dt to ds is greater than 0. We know that d minus p to dv is greater than 0. We know that d mu t to dn is greater than 0. Those, what they basically say, you see, the behavior, it's not only that the intensive parameters are the same. It's also how they're going to modify due to some interactions between those two phases are also have to be satisfied by our stability criteria. Okay. So next we want to see what happens at this equilibrium between phase A and phase B. Now, you already know that in order to describe those two phases, we need to use something that is exactly the same for phase A and for phase B. Those are our intensive parameters. So what we want is to describe the coexistence between the phases while using intensive parameters, so T and P and mu. Why those parameters? Because I know that when those two phases coexist with each other, the parameters should be exactly the same. So my quest here is how I can describe the different connections between T and P and mu. Okay. How those are related. So in order to do that, to find this connection between the intensive parameters, I need an equation. So this equation, maybe you've heard of it from thermodynamics class is Gibbs-Duhem equation. Have you seen it? No. Okay, I'm going to derive it anyway. So I want to derive some connection between those two. This is why I'm going to make some tricks of dE equals TdS minus ddV plus mu dN. So this is the only general equation that I have. I have some other connections about stabilities, minima and maxima of energy and entropy, but I have to start from this equation because here I have some sort of connections between intensive variables or extensive variables and some intensive variables. So what do I want to do? First of all, I remember that energy is extensive. Okay. So what does it mean? First of all, it means the following. So if we take and so our variables E is a function of S and V and N. I'm assuming that I have only one type of molecules for simplicity, but the same trick can be played if I have additional molecules. It's going to be only modified by mu1 dn1 plus mu2 dn2, etc., etc. We only have one type of molecules. It's sufficient for our purpose. So I'm asking the following. What happens if I take and modify or simply multiply everything by lambda? So S go to lambda S, and V goes to lambda N, lambda V, and N goes to lambda N. Now, lambda is some parameter. What are those transformations mean? I'm rescaling my system. See, so I'm making the entropy larger by a factor of lambda. I'm making the size of the system larger by the factor of lambda, and I'm making the number of particles in the system larger by the number of alpha. So what's going to happen to my total energy? Okay. So basically I can use this equation, okay, with those new parameters to see what is going on. So dE, it is T is not modified, I only rescaled the entropy, D lambda S, or this is E prime. So E prime is a function of lambda S, lambda V, and lambda N. So D E prime, it's T D lambda S plus, minus P D lambda V plus mu d lambda N. Lambda is some constant, so I can take it out of the differential over here, and over here, and over here. So I'm saying that d prime is lambda t ds minus lambda p dv plus lambda mu dn. Okay? And we write it down as de prime equals to lambda de, or we basically can say de prime equals d lambda e. This is the property of extensivity of the energy. Okay. Because what is written over here is that E of lambda S, lambda V, and lambda mu, not mu, lambda N equals to lambda E, S, V, and N. If I rescale all my intensive parameters, including entropy, the energy is basically rescaled by the same factor. Now, this form in mathematics have a special name. So if I have a function, and A is some general function, and I rescale all the variables of my functions by a constant parameter, okay, and in response, all what happens is that my function is simply rescaled by the same parameter. Okay. What's the name of this function? Well, homogenic. So E is homogeneous, I think. Homogeneous of first order. So there is a whole theory of homogeneous functions of any given order. So in general, if I have function g lambda x, which is satisfied lambda to the power of n of g of x, g of x is homogeneous of order n. Okay. So what you have seen that energy is a homogeneous function of the first order. Now, why it's important, why it's convenient? Because there is a theorem for homogeneous functions of the first order. Okay. So for homogeneous function of order n equals 1, what we know is basically g of lambda x1, lambda x2, lambda x3 equals to lambda g x1, x2, x3, etc. Okay. So this is just a definition of homogeneous function of first order. But Euler theorem, Euler proved, so this is the Euler theorem for homogeneous functions of first order, that g of x1 and x2 equals to a sum over I dg dxi multiplied by xi. I won't prove it to you, but it's not so difficult to show it. You need to be Euler to show it for the first time, but it's not there really hard. But we now can use this theorem for energy, right? We can say that energy, which is a function of S, V, and N, is what? It is the derivative of energy with respect to S multiplied by S plus the derivative of energy with respect to V multiplied by V plus the derivative of energy with respect to N multiplied by N. Okay, so what it is, S, V, and N. What is dE to ds? T. S. What is dE to dV? Plus, minus P, V, dE to dN, mu. So unless something really bad happens as a phase transition in between, energy, when it's defined force for equilibrium, can be displayed in this very simple form. Why? The only thing that we needed is, well, this first law and the property of extensivity. This is enough. Now, why do we need it? Remember, our quest was here to obtain some sort of connections between P and V and mu. We want to use this equation in order to obtain those relations. Yeah. Everything that we are doing in thermodynamics is in equilibrium. And everything that we should do during this class is only for equilibrium.
But which steps that we did here requires us to be in equilibrium?
what steps? Basically transition from one state to another. E, this guy, was described only for equilibrium states. Okay? So when we have written this equation, you remember I plotted this, basically this guy. Okay? How high this guy is in this equation. I obtain it when I assume that I have two states that are in equilibrium, and I have some quasi-static, adiabatic, reversible process that I connect those two states by this path. And then I made a flip-flop in the air and said, well, I don't care about the process because I only care about the final state and the initial state. This is why this equation and this relation is only for equilibrium states. Great. This is the goal. How we connect or make some sort of a connection between the intensive variables, intensive parameters. So, yes?
Instead of V, it should be temperature, because you want to keep...
Yeah. Thanks. Great. Yeah. Intensive parameters, not extensive. Great. Thanks. Okay, so I'm going to use this equation in order to obtain something which is called Gibbs-Duhem equation. Equation. So I have E, which is equals to Ts minus PV plus mu n. And I'm going to compute the differential of the left-hand side and the right-hand side. So on the left-hand side, I have dE. On the right-hand side, I have d of Ts minus d of PV plus d of mu n. So what is d of Ts? It is s dt plus t ds minus p dv minus v dp plus n d mu plus mu dn. This is great. What I have on the left-hand side? On the left-hand side, I can use the thermodynamical law that I already used, which is TdS minus PdV plus mu dn. Right. So dE, we know, equals to this one. The right-hand side obtained by taking the differential from this expression. Okay. Now, what do we do? TdS, minus PdV minus PdV, plus mu dn plus mu dn. Okay. So we are left with, I haven't crossed something properly. No, this guy.
Yes.
Yeah. Three on the left hand side. Thank you. Yeah, this is good. So, what we have? We have n d mu, we have plus s dt, we have minus v dt. This is Gibbs-Duhem equation. Okay, why it's important? Well, we can write, for example, for the chemical potential, d mu equals minus s divided by n dt plus v divided by n dp. Okay, so you can see that now I'm connecting mu, which is an intensive parameter, to t and to v. Okay, so what is known? I can write that mu is a function of t and p. Okay, and I also know that d mu to dt equals to minus s divided by n. And I also know that d mu to dp equals v divided by n. You can say, well, Stas, so what? Right, so all the class on thermodynamics, you obtain that some variables are derivative of some other variables, and it's not really clear what this all means. So I have some sort of a derivative. Yeah, if I take the derivative of mu with respect to t, I obtain this, it is s divided by n. By the way, mu is intensive, t is intensive. So on the left-hand side, I should have some intensive quantity. What I have on the right-hand side? It's intensive or extensive?
It's extensive divided by extensive.
Intensive or extensive?
Intensive.
Intensive. Extensive divided by extensive, it's an intensive variable. Okay, the same goes for this guy. Now, this is actually very important. Why it's important? So not only those derivatives, but the thing that we have mu is a function of t and p. Why it's so? Because I can now say the following thing. Remember, the quest, again, is to describe some sort of phase transitions, right? So I know that in phase transitions, mu should be equals to, in one phase, to mu in the other phase. T in one phase should be equals to the other phase, and P in one phase should be equal to the P in the other phase, right? So this equation somehow should describe phase transition, maybe. Now, an additional physical fact that we bring from experimental observations. We see that phase transition usually occurs with some abrupt change. Right? So the transition from vapor from water to ice. We've seen those all in those YouTube videos. Suddenly, all the bottle, and really fast, actually transforming from one phase, very liquid, you can shake everything, to a solid, and it actually solidifies extremely fast. How does this happen? So there is some abrupt change. But we should say, well, but everything should be continuous, right? So how can it be described that from one point of view, experimental point of view, we see some abrupt changes, we do not quantify them, but we see them in experiments. The theory tells us, at least this thermodynamical theory, everything is continuous. Okay, so what happens? Or how I can basically make those two facts live happily with each other. So the solution is quite simple. So if I have three axes, one is P, the other one is P, and the third one is mu. So mu, yes. I'm trying to reconcile the fact that phase transition occurs abruptly, and the fact that thermodynamics says that everything is continuous. Okay? All right. So if mu is a function of t and p, basically says that mu is some sort of a two-dimensional manifold, okay, determined by t and p. So I can plot it as two-dimensional sheet that goes like this. And I can say, well, this part of T and P's describe phase A. Now phase B, how are we going to describe it? So phase B, we can say, it's also some sort of a two-dimensional manifold. Right? So this is phase B. Now you see I can cross from this manifold continuously, nothing really bad happens to phase B, okay? Except that there is a line. I hope you can see this, but this line that separates those two phases, and although mu is continuous, right? So mu, nothing bad happens to mu, it's continuous. There is no jumps, but there could be a jump, not in mu, but in what? In derivative of mu. Okay, so simple fact from a mathematical point of view. So the function can be continuous. When the derivatives are not continuous, there should be some sort of a jump, or can be some sort of a jump in the derivatives. So therefore, there can be an abrupt change if you look on the derivatives. But the function itself is a continuum function. Okay. So what we expect that a transition from one phase to another, it indeed happens in smoothly when you're looking on one quantity, such as mu, but it's going to be described by jumps, abrupt changes in other quantities which are the derivatives of mu. Okay. So this is already nice, right? So we do have some sort of a mathematical theory. Not everything is continuous. So yeah, the functions are continuous, but the derivatives are not. And the points when those derivatives are doing something funny, like jumping, this is the point of phase transition between phase B and phase A. Now, let's look on the derivatives. What actually is jumping? So we have d mu to dt can jump. Okay, and we have d mu to dp, which is v divided by n, can jump. One is easier to explain than the other, but we can try both. So what is S divided by N? So we already said that it's an intensive quantity. So this is the total entropy of the system divided by the total amount of particles inside the system. So let's call it S with those lines. So this is entropy per particle. Entropy per particle. What is this? This is the total volume divided by the total number of particles. So this is volume per particle, right? Volume per particle. So what we see that in phase transitions, okay, there is a jump. We can say mathematically there is a jump in derivative. We can understand that there is a function and the derivatives are not continuous. The function is continuous, but the derivatives are not. So what happens when the derivatives are not continuous? We experience a jump. What is the jump? The jump is in entropy per particle. If we look on some random particle inside the system, its entropy, which is not still clear what it is, but its entropy abruptly changes from one value to another. So if we associate entropy somehow with the mean kinetic energy, so the particle is rattled like this on average, it suddenly stops rattling, or almost stops rattling. Right? So think about crystallization, or turning of water to ice. We have a lot of molecules inside the system. All the molecules are doing something, and they're wandering from one place to another. The system solidifies like that when we cross the critical temperature. What happens to each and single molecule? It cannot just move in every way around. So those rattling is suddenly, very, very, very sudden and very, very fast, basically turning from something like this to something that it's not moving. I cannot move my hands in parallel. So this is for the entropy. Okay. The volume, the same thing. So I have this my particle which is wandering around, and its effective volume, it's not only this small ball that represents my particle. It's also where it wanders. So it was wandering in this area, and now it's wandering in this small area. And again, this happens abruptly, and we see this on microscopic scale. It's not something that happens only for a small amount of particles. It happens to the whole system, and really, really, really fast. Okay, so those are the jumps. This is why we call it a phase transition. There are functions that nothing really happens to them, but the derivatives can be discontinuous, and this discontinuity describes a phase transition. So, a phase transition where those quantities are actually jumping is a phase transition of first order. First order phase transition. So what happens at first order phase transition? The first order derivatives are discontinuous. But we can imagine a system where we have mu as a function of t and p, where the mu is a continuous function. The first order derivative of mu is also a continuous function, but the second order derivative of mu can be discontinuous. Right? We can think about of a function, general function, that is a function of t and p, that the derivatives are continuous, but the second derivatives are not, at some points, on some lines. Right? So this is not going to be first order phase transition, but second order phase transition. Phase transition. Second order derivatives experience a jump, or are discontinuous. Are discontinuous.
אפשר שאלה סטאס?
Sure, question.
לגבי זה שהנגזרת לא רציפה, אני לא מצליח לראות, אני צריך להבין את הדוגמה שהבאת, אבל הנגזרת היא מינוס S. אני לא רואה למה זה לא רציף, כאילו, אם אני מוסיף דלטה S, עדיין זה, למה זה לא רציף במתמטיקה?
Okay, so the question is why I can say that the derivatives are discontinuous. My claim is the following. On this line, this phase A is in equilibrium with phase B. Exactly this on this line. What happens when mu and t and p are at this point over here? So exactly at that point, I can bring two systems in a contact. This is going to be liquid. This is going to be vapor. I will place them in a contact, and nothing will happen. Absolutely nothing. Okay, so this is the phase separation line. Exactly on the phase separation line, okay, two systems can be in equilibrium and coexist. Right? But there is a difference. You see it with your eyes that there is a big difference between liquid and vapor. Something happens, right? So I infinitesimally cross from this point towards phase B or towards phase A. I modify something. I modify my temperature. I modify my pressure. I modify my chemical potential. Something. And all of this coexistence disappears. Everything becomes vapor. Abruptly. So the only way that I can say that a change, an abrupt change, can occur is that my derivatives are discontinuous over here. Right? Now you can say, well, yeah, why not? T and P and mu cannot be discontinuous because of the stability. They have to be equal between the two phases. But S can be discontinuous, and V can be discontinuous, and E can be discontinuous. Right? So this is why I'm saying if there is an abrupt jump, something should abruptly be modified, and those somethings are the derivatives. You can say, well, maybe it's not the first derivative, maybe it's the second derivative. Well, then I will call it a second order phase transition. Right? Yes?
But wasn't part of the definition of the entropy function that is continuous? Like,
You see, surprise, surprise, it's not continuous. It can jump. It's raising monotonically with energy. That's the only thing that I said. Okay? So it can experience an abrupt jumps when I'm crossing specific points. Right? And it's not affecting stability of the system. So the system can be in equilibrium and the entropy can still be jumped. It's also not challenging the definition of entropy that it can be discontinuous and still monotonic. Fine. Yes?
you're assuming that the phases are in equilibrium with one another, right?
On the coexist. So this is coexistence line. So on coexistent line, mu A equals mu B, PA equals PB, TA equals TB. They are in equilibrium. We have to look on equilibrium systems. Okay. In this class, we are not going to talk about dynamics. So on the way to the class, Nadav Schneer grabbed me. He's going to teach this class in semester back and said, why you're not speaking about dynamics? Why not to speak about kinematic theory? Well, maybe in the second semester you can learn statistical physics with some kinematics inside. Right? The same class. So this is for reserve students that are mobilized right now. Okay. Great. First order, second order, third order. Now, in nature, most of the time that we see phase transition, and the natural phase transition that we are all familiar with is liquid, solid, vapor. Okay, it happens abruptly, and it's a first order phase transition. There are some second order phase transitions which are also called continuous phase transitions because this manifold does not have any kinks in it. Okay, so for example, the transition from ferromagnetic to paramagnetic at zero external field is second order. Superconductivity also appears as a second order phase transition. So there are different systems. In some of them we see first order, in some of them we see second order. But this is what interesting, something really nice, interesting, surprising happens in this small region. Over here, yeah, we have everything is continuous. We have this first law, B equals to S dt minus PdV, and you can heat the system a little bit, you can cool it, you can build Carnot engines, whatever you like, but something really, really novel happens on this line. Now, the moment that we have this, we should describe this line a little bit better. So what happens on this coexistent line? Because maybe we cannot understand the whole physics of whatever is going on inside, because we know that the change is fast and abrupt, but maybe we'll later. But at least we can now define the coexistent line, right? So in general, if we look on t as a function of p, fine. T, p, and t. We know that there should be a line that separates phase A from phase B. And this line we call coexistent line. Now, how do we know that this is exactly a line? Well, because we know that mu A of P and T equals to mu B of P and T. So this is somehow relates P and T. This is an equation of P and T, and basically the solution is a one-dimensional object like a line. So this is why, because of the this constraint, you can say, that happens at the phase transition, we know that there is a single line, okay, a single line that separates one phase of matter and the other phase of matter. You can ask me, Stas, but for example, for liquid, there are three phases of matter, right? So there is liquid, vapor, and there is solid. So maybe there is something more. Maybe there is also phase C. Phase C. Right? And indeed, there is also phase C. There is a coexistent line that separates phase B from phase C. There is a coexistent line that separates phase C from phase A. And there is one single point, okay? And at this specific point, which are very specific P and very specific T, that you can go directly wherever you like. You can go to solid, you can go to liquid, you can go to vapor, wherever you like. Why is there is only one point? Because mu A pt equals to mu B pt equals to mu C pt. So basically there are two equations. One that connects mu A to mu B, the other one that connects mu B to mu C or mu C to mu A. So we have two equations and two variables. So P there is should be only one single solution. Very specific P and very specific T. Great. So there is a coexistent line. How do we find this coexistent line? It is nice to know that there is a coexistent line. But what actually happens? How do we find it? So let's look again on this diagram of P and T and plot this line on top of it. Okay, so if I'm computing, the change of mu, so I have one specific mu over here. This is mu A, this is mu B. Okay, and this is mu A, and this is mu B. And I'm still on this one single line. And I'm moving from one point on this coexistent line to another point on the same coexistent line. What happens? So first of all, I know that d mu equals minus s dt plus p dv. So when I shifted from this mu, from this point at phase A, or I shifted from this point to that point on the coexistent line at phase B.
That's the forgot the n.
I forgot the n. Great, but let's write it like this.
זה VDP, לא?
First of all, it's VDP. VDP. So we write it down as S per particle and V per particle. Okay. Thanks. Now, so what happened over here? So the modification, or the delta mu on this hand side was what? Was minus S A dt, okay, plus P A d v. D V A d t. Right? So this is delta mu A. On phase B, delta mu D equals to minus S B dt plus V B dt. So this what occurred to the chemical potential when I was in phase A. This what occurred to the chemical potential when I was at mu B. But at the coexistent line, mu A equals to mu B over here and over here. So delta M mu A equals to delta M mu B. So we can have minus SA dt plus VA dP equals to minus SB dt plus VB dP. Okay, so we have dP VA minus VB equals to SA minus SB over dt. So dP dt equals to SA minus SB divided by VA minus VB. The equation is called Clausius-Clapeyron equation. So if I know about how much my entropy have jumped and by how much my volume have jumped, right, I can understand or I can find the equation for how P at criticality at the coexistent line is modified with T at criticality. So this is the equation. This is a differential equation for the coexistent line. I can find how P C, which defines the critical pressure, is modified with the critical temperature by looking on the difference at the entropies or looking at the difference of the volumes. You can say, Stas, I don't know how to measure difference in entropies. Well, if everything is in equilibrium, I know that TdS is equal to dQ. So I can maybe measure heat, and by changing or by looking by how much the heat have changed from when going from one phase to another, I can compute something about this coexistent line. So we'll see examples in your homework or during TA classes. Thank you. That's all for this week. See you next Sunday.